Okay, hello everybody. Again, we have to explain today the third session of Chapter 6, which is about weak acid and weak base. So let's start by listing our objectives. Today we have three objectives to be covered, which are, first of all, to determine the acidity constant Ka of an acid and Kb of a base, as well as the corresponding pKa. The second objective is to compare the acidity of many weak acids, and the last is to calculate the pH of a weak acid solution and of a weak base solution. So let's start first of all by the first objective, which is about Ka. The acidity constant Ka, if we have to consider so far an acid, let's consider the dissociation of ethanoic acid in water. That is highly repeated example. It's CH3COOH that reacts in water or dissociates in water in a reversible way, producing H3O+ and ethanoate ion. This is a reversible equation. So we knew from our equilibrium lesson that when reaching equilibrium, we have something called K, which is the equilibrium constant. So deal with this equation normally, as if it is a reversible equation, and calculate K. So simply by applying the formula of K, we have to say that it is equal to the concentration of each of the product here, power the coefficient here, the coefficient each product has. But here in our equation, or in our reaction, all the products and reactants have here a coefficient by 1 of 1, 1, 1, and 1. So simply K will be the concentration of the product COOH minus multiplied by the concentration of the second product over the concentration of each of the reactants. But water in this case practically has a concentration that is constant. So we can eliminate water from here and replace it by a constant. We obtain thus what do we call Ka. So Ka, it is the conjugate base of the acid multiplied by the concentration of H3O+ produced by the acid over the concentration of the acid, and this is something to be taken from now and then. So once we say Ka of an acid, even without writing the equation, we can directly write it in that way. The conjugate base, as we said, from the acid multiplied by the concentration of H3O+ produced over the concentration of the acid at equilibrium, or we can refer also to the equation, and this is Ka. Ka is called, as I said, the acidity constant of the pair CH3COOH, CH3CO minus. As usual, Ka depends only on temperature. For example, for this pair, Ka equal 1.8 times 10 to the power minus 5, definitely at 25 degrees Celsius. So this is Ka. Now let's consider the case of a base. Look at this base, CH3CO minus. Now why CH3CO minus? The ethanoate ion is a base. Simply because look at that equation. CH3CO minus takes H plus from H2O to transform into the conjugate acid. So since it took H plus from H2O, it means it acts as a base according to Bronsted, and water here, H2O, donates H plus, so water acts as an acid. So this will be considered as a base. This is an acid. This will give the conjugate acid, and this will give the conjugate base. In this reaction, as I said, the ethanoate ion is a base, since according to Bronsted, it accepts H plus from H2O. For this reversible reaction, also let's consider it as a normal equilibrium, and let's find the constant, the equilibrium constant Ka. That is also here, it's an application of the formula, the concentration of the product multiplied by the concentration of the second product. Take into consideration that the coefficient here is 1 and 1. This is 1. We will not find here exponent anything, over that of the reactant, exactly as we did in the previous slide. In the same way, H2O is practically constant, so we can eliminate it here, or not eliminate it. After all, it can be replaced by a constant that we will multiply by K here to obtain K prime after eliminating H2O to be here, the constant it means. So we will obtain simply these three terms alone. Now we have to do something. We have to multiply the numerator and the denominator in K plus by the same value, which is the concentration of H3O+. This is calculation, not more. So we will obtain, as you can see here, it is in red. This doesn't change at all the constant K prime, but here look, pay attention to this. OH minus concentration times H3O+ concentration, it is actually K water, the ion product of water seen previously. So this value here can be replaced simply by K water. And look at this, it is actually the inverse of the K acid studied or seen in the previous slide. So بكل بساطة K prime, which is called KB, it is equal to this. It means we can say K acid times KB, it is KW. This is KB, can you see? This is KB, this is KW, and this is K acid, that it would be here in the numerator as we saw here, and then K base times K acid would be equal to KW, and this is applicable for all acid-base pair. So this is our first objective. Now, how to make use of Ka, or before we have to study also something about pKa, the notion of pKa. You know that pKa, in the first lesson, it has taken as the following. Did you remember when we did minus log Kw? Kw is equal to 10 to the power minus 14, so pKw is equal to 14. It's something admitted. Now, in general, everything denoted here by x, let's say, for which we apply the mathematical function minus log, okay, the result would be pKa of this, of this x, regardless the nature of x. So in this case, our x was Kw, it becomes pKw, and in this lesson, minus log Ka would be equal to pKa in a similar way. Simply, we are creating, not me, it means chemists have created pKa in order to avoid working with numbers like 10 to the power minus 14. It's easier to use, for example, 14 instead. This is simply the aim of creating or of using pKa. As I said now, how to make use of Ka, Kb, and pKw, or pKa in general. We can use it in order to compare the relative force of acids and bases. How? Consider the pair here. Pay attention. It is the methanoic acid, HCOH, and methanoate ion, which is also a weak acid. What do we have for this pair of acids? We have the following. We have H3COH that dissociates in water in a reversible way, producing H3O+ and HCOO-. Now, as given, it means measured by scientists, Ka1 for this acid, for this couple, it means Ka1 is equal to 1.8 times 10 to the power minus 4. Definitely at all values here will be at 25 degrees Celsius, but we will not repeat this tip again. Now another pair, which is the ethanoic acid, you know it well, and ethanoate, also this reversible reaction, the corresponding Ka2 for the couple ethanoic acid, ethanoate, it is 1.8 times 10 to the power minus 5. Let's compare now Ka1 and Ka2. Look here. Ka1, which is that of this pair of methanoic acid, is greater than Ka2 of the ethanoic acid. What does this imply? This implies that the methanoic acid dissociates more than CH3COH. Why? Because when Ka is greater, it means, according to the formula of Ka, in the numerator we have more products that are produced with respect to CH3COH. It means HCOH, upon being dissociated, produced more H3O+ than CH3COH, and the acidic or the acid character is due to H3O+. Each time we have more H3O+ that are produced, it means the acid is stronger, and this is why we can directly say that HCOH is stronger than acid CH3COH based on a Ka. How to generalize this? Simply, when Ka increases, the acidity increases of the species we're talking about. Now, from Ka1, we can apply minus log. So pKa1 would be equal 3.75. Can you notice that this number is easy to be handled with respect to 1.48 times 10 to the power minus 4. This is why, as I said, scientists use pKa sometimes instead of Ka sometimes. And here is Ka2 for the pair of ethanoic acid. So the pKa is 4.75. As you can see, pKa1 is smaller than pKa2. So also here we can generalize it. When pKa increases, the acidity decreases. Here they are inversely proportional, and here they are proportional. This is how to use this in order to compare the relative force of acids and bases. Now, for strong acids. A strong acid in general, here considered HA, dissociates completely in water according to the equation, and pay attention that the equation is not reversible, it's a complete one. So HA plus H2O will give me H3O plus and A minus, which is the ion. At the beaker where the reaction occurs here, there is no more HA. Why? Because HA has dissociates completely. It means there is no more HA at the end. What do we have in the reactional medium? We have only H3O plus resulting from the dissociation, that is a strong acid. A minus, that is a spectator ion, and H2O. Now, A minus is a spectator ion, as we said, or sometimes called indifferent ion. It means it has no tendency to react, to accept a proton. Thus, theoretically, it acts as a conjugate base that is extremely weak. H3O+, this species here, can react with water molecule according to the reversible equation, because it slowly reacts with it. Not slowly, after all, it's in a very small amount, we can say, or rate. H3O++ plus H2O, reversibly, it can react with this one. Now let's calculate Ka. Ka, by definition, according to what we have seen in the previous slide, it's equal to H3O+ over H3O+ here. So theoretically, not theoretically, after all, it is almost equal to 1. And this value is to be generalized for all strong acids. It means the acid-base pair involved in this case, it's H3O+ and H2O. Why? Because this is the acid and this is the corresponding base, or the conjugate base. So Ka for this H3O+ H2O, that is equal to 1. And this couple is to be considered for all strong acids, whether we're dealing with HCl, with an HNO3. Okay, this is applicable for all strong acids. They have H3O+ and H2O. We will not anymore consider, for example, the ion corresponding from each of them. And pKa for this couple, which corresponds also to the strong acids, it's equal to minus log Ka. It means it is 0. For strong bases, in a similar way, let's consider a base that dissociates completely in water according to the equation. Can you see? It accepts H+ from water, so this is a base and this is the corresponding acid. This is the acid and this is the corresponding base, and the reaction is complete. At the end, in the same way, there is no base in the medium because, as we said, it dissociates completely. There exists only BH+, that can be considered as an acid that is extremely weak. We have also OH-, that is a strong base, and H2O. Again, the single chemical equilibrium that will occur is between OH-, H2O in a reversible way. So here also, let's find Kb. It is equal to OH- concentration in the product over that of the reactant. They are equal, so it is equal to 1. Now refer to the previous formula, Ka equal K water or over Kw. It would be equal to 10 to the power minus 14. Now, what is the acid-base pair involved in this case? In case of a strong acid, we have H2O, that is the weakest acid in the world, and OH-, that is the strongest base in the world. And as I said, Ka will be, for this couple, will be equal to 10 to the power minus 14. And this is applicable for all strong bases, and the same for pKa, which is 14. Now for strong acid and strong bases, don't use all these details. This just has to be explained once to understand where did we get these values from. As for later, you can refer to what do we call the pKa axis. Pay attention to this. Here is the pKa axis. The pKa, it varies from 0 till 14. here are the extreme values of pKa. Now the increasing strength of bases goes up and the increasing strength of acids goes down. Pay attention that in the pKa axis here to the left we will write everything related to the conjugate bases of the couple, and here to the acid of the couple. Now the highest pKa 14 is for the strongest base, which is represented by HO minus, and here it corresponds what? The weakest acid. Now for any other couple we can write here the weak base and here the weak acid it means in the couple, and below here we have here the weakest base in the word, which is H2O, versus the strongest acid, because as I said, increasing strength of acid. So all strong acids would be represented in that way and the base in that way because the increasing strength of bases. This is to be memorized by heart. It would be used in all exercises almost. Now, how to determine the pH of a weak acid? This is our third objective. We have to keep in mind that for any solution, whether it's a solution of strong acid or weak acid of a neutral, this formula is valid to calculate the pH. pH equal minus log of H3O plus. So our concern in any case when we have to determine the pH is to determine the concentration of H3O plus released. Thus, in a weak acid solution, the initial concentration of the acid is greater than the concentration of H3O plus obtained because there was no complete dissociation. So the pH is different from minus log Ca as we saw previously. Thus, to determine the pH of a weak acid solution, we have to find first the concentration of H3O plus, and then we will apply this formula and we determine the pH. How to do it? Consider the example. For example, in an exercise, I'm asking you to determine the pH of a solution of ethanoic acid having an initial concentration 10 to the power minus 2, and as given, I give you the pKa of this pair, which is equal to 4.75. What do you have first of all? We have to draw the table of conversion. At T0, I'm copying just the value, 10 to the power minus 2, 10 to the power minus 2, and here definitely 0, 0. Pay attention that water will not be considered because its concentration is practically constant. At equilibrium, CH3COH dissociates by minus X, and thus we will obtain here X and here X. Now, let's say for about Ka, since we have pKa, we can find directly Ka. Ka is equal 10 to the power minus pKa. Why? Because pKa is equal, because pKa is equal minus log to Ka. So Ka will be mathematically 10 to the power minus pKa, and it is found to have this value. Okay, now applying Ka, the acidity constant, Ka, it is equal, as we said, to the concentration of the conjugate base times the concentration of H3O plus over the concentration of the acid at equilibrium. According to the table of conversion, here it's equal to X, here is equal to X, and the initial concentration by given it is given as 10 to the power minus 2 and minus X, that is here. So knowing Ka, it will be replaced here and we will obtain a quadratic equation of X. Using your calculator you can find actually two values of X. One of them would be rejected because it would be negative. You have to do this calculation to be convinced, and the second, which is this one, is to be accepted. So this is X. Actually, there is another way. Here we can neglect X in the denominator because Ka is less than 10 to the power minus 4, but what am I saying now will be postponed to the next lesson, to the next session after all. So here, as I said, we have two values of X. This is accepted. Giving X, I can directly determine what the concentration of H3O plus produced. So pH equal minus log of H3O plus equal minus log of X, so that is found here, equal 3.37, and this is how to determine the pH of a weak acid. Now, keep in mind that each time you have to determine the pH of a weak acid solution, you have to follow the below steps. First, start writing the equation of dissociation of the acid in water. Second, draw the table of conversion in terms of X. Third, find X using Ka or pKa, it's the same. And finally, calculate the p-value of pH applying the formula pH equal minus log H plus. Now, how to determine the pH of a weak base in a similar way. Here also, you have to remember that for any solution, strong or weak acid, strong or weak base, you can use this formula that derives from what? From pH equal minus log H3O plus. So pH equal, but it's easier because here we have a base, it's easier to use this formula. pH equal 14 plus log concentration of OH minus. Then in a weak base solution, you know that in the same way Cb, the concentration, the initial concentration of the base is greater than the concentration of HO minus. So pH is different from minus log Cb. It had to be different from 14 plus log of OH minus, sorry. Thus, to determine the pH of a weak base solution, we have to find first of all the concentration of HO minus. So pay attention to this mistake. Okay, it is different than 14 plus log to Cb. Now, in the same way, we have to consider a solution of CH3COO NaH, which is 10 to the power minus 2 mole liter minus 1. Now, pay attention that CH3COO Na in water is dissociated totally into this ion and Na+. Na+ is nothing as it doesn't exist in the medium for us. So we care about this one that will act as a base in water. How? By accepting H plus from water, giving CH3COH. So pay attention that in exercises we have to give this. Also here there is no H. There is no H after all. It's CH3COO Na simply. We have to give it in that way in exercise like it's written here. And you have to consider U as a base because it is CH3CO minus. Also, the table of conversion, I will not repeat those details. Then, what do we have to calculate? We have to find Kb, that is equal K water over Ka. It is equal 10 to the power minus 14, as you know, over the Ka given here. Okay, because it is found from the pKa, and then Kb would be equal to CH3COH, OH minus, as any equilibrium, as any Kb over the concentration of the base. So it is equal how much? Here it is X, here it is X over 10 to the power minus 2 minus X. So come in here, we have a quadratic equation, and you have to find two values of X where one of them is to be rejected when it is negative, because impossible that this dissociation be negative. And we will accept this value, which is logical, and the pH will be calculated. 14 plus log X, it's equal to 7.9. As an application, please, these three objectives have been covered. You have now to solve the following exercises for this week. You have 5, 6, 7, 8, 9, 10, and 12. 12 is the most complicated one, but it's okay. These are small exercises, and they are on your textbook to page 158, 159. The solution, as usual, will be uploaded. And thanks for your